What is short circuit? Short circuit is accidental or intentional conductive path between two or more conductive paths. That means it could be an intentional, that means we can create that, or it could be an accidental because of something else. And the conductive path is because of the failure in the insulation, and which brings the voltage between these two conductive paths to zero if it is a dead short circuit or bolted short circuit, and or at least to smaller voltage if it is an arc fault, right? So what is short circuit? It's an intentional or accidental conductive path between two conductive paths, so that reduces the voltage between these two paths. So that's a short circuit. Why do we need short circuit study, or why we are talking more on short circuits? In practical power systems, it's not commercially viable to construct a power system with 100% free from failures. So even if somebody argues technically that is possible, but that may not make a commercial sense. So that's the reason why we need to study short circuit, and we need to ensure the equipments in the electrical power systems are capable of withstanding this short circuit for a short time, at least till the relay clears the fault. Okay, what are the effects or impacts of short circuit? As I told, even in a well-designed power systems, there is a probability for a short circuit. So this short circuit results in a large current, and of course, this current decays over the period. And it results in a huge thermal stress, and because if there is a fault, the current might be 50 times or 100 times of the full load current. So definitely it creates a thermal stress. And of course, it creates electrodynamic stress as well on all electrical power system equipments. So the short circuit may lead to an undesirable current flow, the current flow which is not really desired for the system. It's excessive in magnitude, and it results in an equipment damage thermally. And sometimes this short circuit may result in over voltage also. So few people may get a surprise why there is an over voltage. So if it is a non-grounded systems or resistant grounded systems or resonance grounded systems, which is also called as Peterson coil system. So in this case, if there is a single line to ground fault, there is a probability that the healthy phase voltage can be much higher than the expected voltage. So which we are not generally discussing much about it, but still such excessive over voltage has to be studied in detail, at least for nuclear power plants. And definitely this short circuit is hazardous to working personnel, and this short circuit in specifically high voltage and extra high voltage systems may result in generator out of step. That is basically an angular stability which has to be covered as a part of transient stability. So these are the effects. So in order to mitigate this or minimize these effects, we need a short circuit study. So these are the types of faults. The faults can be considered as series faults and shunt faults. Means most likely when we talk about faults, that fault we generally tend to think that faults are like shunt faults, but there is a fault called a series fault as well. The classification of series fault is single conductor open and two conductor open. So probably the image below here shows the single conductor open. So here you can see three phases, out of which only two phases are connected, and the third phase or the first phase, whatever you call, that's open. So the typical example of the single conductor open is broken conductors where this broken conductor is unable to touch the ground. So that's the open conductor. So similarly, there could be a two conductor open as well. So if two phases are open, then this is two conductor open. So this results in a huge negative sequence. The series faults results in a huge negative sequence as well as over voltage. So how the shunt faults increasing the current? So similarly, the series fault increasing the negative sequence and the voltage, which is essentially has to be studied at least for nuclear power plants. Okay. So our focus is not series faults today. So we are focusing more on the shunt faults. Shunt faults can be majorly classified into balanced faults and unbalanced faults. When we say balanced fault, it could be like a three-phase fault or three-phase to ground fault. So here when we say fault is balanced, even the balanced faults may result in unbalanced currents if the network just prior to the fault is unbalanced. So means even if the fault is a three-phase fault, but just prior to the fault, if R phase voltage is different from Y phase voltage, then the current in R phase and Y phase not necessarily same. But means we are making an assumption that generations is balanced, transmission network is balanced, as well as the loads are balanced for this short circuit studies. Most of the times, so when we say balanced fault, means we are analyzing only one phase, means we are assuming that current in all other phases remains same. Then comes to the unbalanced fault, that could be a line to ground fault or line to line fault or line to ground fault. So in order to analyze the unbalanced faults, we may need a sequence components like a symmetrical component theory or Park transformations to find out the currents. So this is a typical examples of different faults. This is an image which is from IEC 60909. So we have in the left corner, we have seen three-phase fault. If we assume the network is balanced, source is balanced, loads are balanced, and the fault is also balanced, then three-phase fault and three-phase to ground fault means have the same current, because in a balanced system, there will not be any current through the neutral. So either three-phase fault or three-phase to ground fault has the same current and it is balanced, and there will not be any current in the neutral if the system is balanced. That's the first one. And second one is an example of line to line fault. And third one is line to ground fault. And the last option, what you're seeing in the image, is single line to ground fault. So what's the objective of short circuit study? So I mean, generally we have two ratings for each and every equipment in the power systems. One is called continuous rating. Say example, if you take a switch gear, you are calling 2500 amps, 4000 amps, 1200 amps. This is a continuous rating of that switch gear. If you talk about 2.5 MVA transformer or 5 MVA transformer, this MVA is the continuous rating of that transformer. So means each and every equipment in the electrical power system has its continuous rating that has to be validated against the load flow analysis. So there is an option to validate the short time rating as well. So there is something called a short time rating for all equipments. If you see 40 kA for 1 second or 31.5 kiloamps for 1 second, so that is basically the short time currents or short time rating of that equipments. This short time rating of the equipments has to be validated by the short circuit study. So the first objective of the short circuit study is to identify or validate the short time rating of all electrical power system equipments. It could be a transformer, it could be a cable, transmission lines, generators, motors, switch gears, current transformers, circuit breakers. You take any electrical power systems that has a short time rating in terms of both voltage as well as the current. So the short time rating of all the equipments has to be identified in the short circuit study. Then it is important for the interrupting equipments like circuit breakers or contactors to break this short circuit current without any issues. So means when you are selecting this interrupting equipments, you need to validate the breaking current, making current, and DC breaking current, which we are going to discuss a bit more in detail in the upcoming slides. So as we discussed, there could be an increase in voltage during single line to ground fault in an ungrounded systems or resistance grounded systems or resonance at resistance. So we are has to see what is the rise in the voltage also during this faults. Okay, why all this we need? Because faults cannot be prevented in a real time. So at best what we can do is we can attempt to mitigate to certain extent and contain this potential hazards or damages because of this short circuit. So as the name says, short time rating means this is only for a very short time. So means then the protection equipment has to isolate that well within this time. Okay, what are the studies? What are the standards which are available to perform short circuit study? There are famously two standards. One is ANSI and IEC. So ANSI we have a C37, which we are not going to discuss more today. We are just focusing on IEC, that is IEC 60909. IEC 60909 has 5 pods, pod 0, pod 1, 2, 3, 4. There are 5 pods. So means we will touch a bit on IEC 60909. There is another standard as well from IEC, which is 61363. Similarly, there are other standards like VDE, that is means European standard from German, and there is an IS standard. These are all the standards which are available. In addition to that, there are some country specific standard as well, something like a GHOST standard, something like that. So means all these standards remains algebraic, and they are solving linear equations, and hence means you might be able to perform your manual calculations as long as the system is small. So let's talk about the limitations of the standard. As I told, there are ANSI and IEC standards which are globally famous in addition to other standards. So today we'll focus majorly on IEC, not on ANSI, because most of us are working in the IEC standards. So this IEC standard is applicable for both low voltage and high voltage. And the question is, it is only for a 3-phase AC systems. That means this is not applicable for a DC, and it is not applicable for a single phase systems. So it is applicable only for 50 Hertz and 60 Hertz, which mean again, as I told, it will not be suitable for a DC, or even it is not suitable for other frequencies, special applications like 400 Hertz or 16.7 Hertz, something like that. And this is applicable only up to 550 kV, and there could be some special measures which need above 550 kV. Okay, and the serious limitations or the constraints of this IEC comes at the last 3 points. So if there is any single line to ground fault in an ungrounded system, which is isolated neutral, or resonance earth systems, which is also called as Peterson coil or compensated earthing systems. So when there is a single line to ground fault in an isolated systems or resonance earth systems, this standard is not really applicable. And the standard is also not applicable for deliberately created short circuits. If you take like in India, we have CPRI. Similarly, there is a KEMA globally. They are, having a testing stations to test the short time rating of the equipments. So there, the short circuit is intentionally, deliberately created. So this standard is not applicable for such testing stations or deliberately created short circuit currents. And IEC 60909 is not really applicable for ships and aeroplanes. So if you are working on a ship power systems, then probably ensure that means you are not using IEC 60909. IEC 60909 excludes explicitly the ships and aeroplanes. Yeah, this is the limitations. So probably then you can understand where this IEC is applicable. IEC is applicable for all grid connected and isolated 3-phase AC systems. And it is applicable in all the cases for 3-phase fault or line-to-line fault. It is applicable for single line to ground fault in a solidly earthed system or resistance earthed systems, but it is not applicable for single line to ground fault in ungrounded systems or resonance systems. Okay, then probably means before reading the standard, we need to understand what are the assumptions made in this standard. The standard assumes that there is no change in the type of short circuit involved. In a real time, generally, if there is an insulation failure in one particular phase, that could be a single line to ground fault, then probably because of the thermal stress or increase in temperature, that may spread to line to ground fault and finally to 3-phase fault. But the standard assumes there is no change in the type of short circuit. That means if there is a 3-phase fault, it occurs as a 3-phase fault. If it is a single line to ground fault, it occurs as a single line to ground fault, and that remains the same type of fault till the fault is cleared. That's the major assumption of IEC 60909. So the consequence is, in reality, if the fault occurs as a single line to ground fault, and if it is spread as like line to line fault or a 3-phase fault, then the asymmetrical current component could be more, but that's not covered as a part of this IEC 60909. So there is no change in the type of short circuit from the occurrence till the fault is cleared as per IEC. Okay. And second one, during this short circuit, there is no change in the network, which means when there is a fault in the system, there is a probability that in the remote end, there could be some breakers or isolators may change their status. So, but this IEC assumes that during the fault, there is no change in the network. That means the breakers which are closed remains closed, and the breakers which are open remains open across the network during the fault. Okay. Third important point, means it takes the impedance of the transformer at its nominal tap or its main position. So this assumption is okay because we are including the correction factor for the transformer KT for the network transformers. Also means what is it? We are using a C factor, so which I come a bit later. So the impedance of the transformer is referred to the nominal tap. That's what most of the manufacturers will give. So you need not use the impedance at other taps to find out the short circuit study if you use this correction factor KT and if you use the C factor. Okay. Then IEC 60909 assumes the faults are bolted faults. That means the fault is a dead short circuit and it doesn't have any arc resistance. That means there is no fault impedance or a fault resistance which is considered for the faults. So that's the other assumption of the IEC 60909. But anyway, means if you're using some simulation softwares, then probably you can simulate with the inclusion of this arc resistance or arc impedance. And the last most important assumption means all line capacitance, shunt admittances, non-rotating loads such as lights, etc., are excluded except their zero sequence. So if you know how the transmission line has to be modeled for a power system study, you model this transmission line as a nominal pi, that is resistance and reactance in series and capacitance in parallel. But means this for a short circuit, the shunt capacitance are neglected for except for a zero sequence. So that's the other assumption of this IEC 60909. Let me move on. Okay. So let's talk about two important aspects of the short circuit. Short circuit close to the generator, short circuit far from the generators. So if there is a fault, the fault current is limited by the impedance. When we say impedance, that's the generator impedance, transformer impedance, transmission line impedance, network impedance, anything. So if the fault is far away from a generator, so the fault current is limited by all these impedances. In that, the generator impedance is comparatively less. This generator offers a time varying impedance, whereas all other equipments in the electrical power systems offers the constant impedance during the fault. If you take a transformer or a transmission line or a cable, they offer a constant impedance. So if the fault current is limited by these devices, the fault current remains same. So probably you can see here, means there are two different fault currents in this. One is exponentially decaying DC component and other one is a symmetrical component. The symmetrical sinusoidal component remains same, only the exponential decaying DC components comes down, because this fault current is limited predominantly by the impedances of transformers, transmission lines, etc., because the fault is far away from the source. But if you look at the next one, the fault close to the generators, when the fault is at a generator terminal, the current is limited only by the generator impedance. Since the generator impedance is time varying one that changes with respect to time, xt double dash to xt dash to xt. So over the time, it is just not the DC component which comes down, but also this sinusoidal current itself will come down because of the increasing impedance from xt double dash to xt dash to xt. So that's the difference between these two. When the fault is far away from the generator, the current, symmetrical current, that is probably you can look at IK double dash and IK, the magnitude of IK double dash and IK remains same, only DC component comes down. But if the fault is close to the generator, probably you can see IK double dash that is much higher, whereas this IK is much lower. So the fault current will come down with respect to these generators. If you are unable to understand this previous one, so probably this helps. Here we have not plotted the sinusoidal current, but we have plotted the RMS current. If you look at this, I mean, so to say, the current fed from the source, that is far from the generator, that's the grid, which remains constant. But if you look at the fault current fed from the generator, that drastically comes down with respect to time. So this is because the generator offers the time varying impedance from xt double dash to xt dash to xt. Okay. Yeah, probably the question is simple. If you are not able to understand the previous one, here you can easily understand when there is a fault which is far from the generators, that as I told, this fault current is limited by various equipments like transformer, transmission lines, cables, etc. The short circuit current, symmetrical current, which you look at the left hand side, which remains constant from the fault instant till the fault is cleared. So here I have plotted only up to 300 milliseconds, but means the symmetrical RMS current remains same. DC current comes down, that is exponentially decaying DC current comes down, which we will discuss a bit later. But the point is, if the fault is far from the source, far from the generator, then the symmetrical current is not going to come down with respect to time. But if you take the fault at generator terminal, the symmetrical current itself comes down. It starts at 28 kiloamps at 10 milliseconds. But if you look at in 300 milliseconds, in just 15 cycles, the fault current has drastically reduced from 28 to 20. Which means when you're working in an islanded systems, which is not connected to the grid, only few generators are there, then the fault current will not be stable. The fault current will come down with respect to time. So when you're coordinating your relays, you need to ensure that the reduction in the current because of the time from change in impedance of the generator also has to be accounted. So this is, I think, simple comparison which you have understood. When the fault is far from source, the current, symmetrical current remains same. Whereas if the fault is at a generator terminal or close to the source, the RMS current itself will come down with respect to time. So this is what probably you have seen in these two. So this is a simple extract from IEC 60909. So you can just go through that standard also. Right, this is just to validate with the simulation results using ETAP, and you can use any of the softwares, not necessarily ETAP, to validate this. Right, there are some MV switchgear data sheets. So up to what voltage, what short circuit current, what's the peak current, etc., and how that has to be modeled in ETAP. And this is physical MV switchgear. Probably almost all of you are testing and commissioning engineers, so you may aware much better. And probably here you can see, so the rated voltage is 7.2, service voltage is 6.6. 25 kiloamps is the short time withstand current as well as a breaking current, 25 kiloamps for 3 seconds, and peak withstand is 63 kiloamps. So how to model this? So breaking current of the breaker is 25 kiloamps, making current of, or making peak of the breaker is 63 kiloamps. So means when you're selecting this breaker, you have to be bit careful. I means if the actual fault current is less than 25 kiloamps, it doesn't mean selection of this breaker is right. You need to validate at least 3 parameters. One means whether the symmetrical RMS fault current is less than the 25 kiloamps, that is the breaking capacity of the breaker, and peak asymmetrical current is less than 63 kiloamps. So that is less than the making current of the breaker. And also you need to look at what is the DC current which the breaker can break. So generally the MV breakers in a normal case will be able to break about 30% of the DC current with respect to their RMS. That means if you take this 25 kiloamps RMS,
then they may be able to break up, 7.5 coulombs DC current. So you need to check what is the DC current, and the DC current at the instant of breaker opening should be less than that 25 coulombs. That means when you perform a short circuit study like this, and if you get some results, the IB symmetrical fault current has to be less than the breaker RMS current, and this IDC at the instant of the breaker opening should be less than the DC breaking capability of the breaker. And you need to also look at what's the making current, which is not displayed here, which I will come probably in the next upcoming slides. So this is probably for an LV switchgears, low voltage MCBs, MCCBs, air circuit breakers. So the interesting fact of IEC 60909 is C factor. So in a C factor means that needs to be essentially considered for all your systems. Most of the time when you're calculating the manual calculations, you may not aware means the C factor is there. So why do we need a C factor? If you're familiar with ANSI standard, then ANSI standard talks about a factor called pre-fault voltage. What is that pre-fault voltage? Fault currents can be calculated by using the formula current is given by voltage divided by impedance. So impedance of the transformer, transmission lines, cables, everything is known. Even if it's a time varying impedance of the generators, that you can put XT double dash or XT dash. But what's the voltage which we need to take? So if we take it's a 1 per unit or 100% voltage, then do you think that just prior to the fault, the voltage at that particular fault point is 100 or not? That's a question to be answered. In a reality, in all voltage levels, we are allowing some voltage tolerance. That means just prior to the fault, the voltage may be slightly different from 1 per unit or 100%. So what is the voltage tolerance which we are accepting? Based on that, we need to select the C factor. The C factor accounts for just not the pre-fault voltage, which is considered in ANSI or IEEE standard, which considers for voltage variations. It is also accommodates because of the change in the impedance because of the transformer tap change. And as we see, we are neglecting the loads and capacitance. That's what I have told. Except a zero sequence, we are neglecting the passive loads and the shunt capacitance. Because of that, there is an error. So this C factor accounts that as well. And when we talk about the generators and motors, there is a subtransient behavior. So like XT double dash, XT dash. So that also the C factor is considered to accommodate all these assumptions, and it's included. So if you look at this, what's the C factor which we need to consider? Generally, those who are performing power system studies may tend to use 1.1 C factor for more than 1 kV and 1.05 for low voltage systems. But please make a note, means the C factor is based on what's the voltage tolerance which is allowed. So in a low voltage systems, mostly in the like 400 volt or 415 volt systems, we are accepting 10% voltage variations. So in this case, you need to use 1.1 C factor for all the voltages. And if your voltage tolerance is only 6% or less than that, then you can use 1.05 C factor for a low voltage systems. But otherwise, you have to use 1.1 C factor. The C factor comes in the numerator, and it is directly multiplying the current. So probably that's also in the previous slides somewhere. If you have looked at with a 1.1 C factor, the current is probably though I have given 25 coulombs, so probably this occurs at 25 coulombs. Here you can see this 25 into 1.1, 27.5, it's because of the C factor. Yeah, then moving to the significance of X by R ratio, probably an interesting topic. Yes, so here there is a simulation. So there is 11 kV, the grid which we have assumed, that has a short circuit current of 3-phase and single line to ground fault, same as 25 coulombs, and X by R of 14. Here, to showcase the theoretical importance of X by R, I have assumed the X by R as infinite. So I cannot give infinite in software, so I have given just a maximum value. So here, means irrespective of the X by R ratio, the fault current means here I have plotted RMS current. The RMS current remains same. So you can check the short circuit current, symmetrical RMS current has not changed if there is a change in X by R ratio. So X by R ratio, we have taken 6 in one case and infinite in other case, but RMS current remains the same and that doesn't has a change. But if you look at, I have plotted for the same fault, I have plotted the peak current here. So what's the current which you are plotting here is the peak current. So here for the same 25 kiloamps RMS, the peak current is only 64 kiloamps for 14 X by R ratio. And for infinite X by R ratio, it is 70 kiloamps. So if X by R changes, definitely your peak current is going to change. And your exponentially decaying DC component is also going to change. So it means higher the X by R ratio, higher the peak current. That's visible from this table. So I have plotted only for the 11 kV bus. Similarly, you can plot for 14 volt bus as well. So with X by R as infinite, that means for the same RMS current of 25 kiloamps, the peak current is 70 kiloamps. Whereas with an X by R of 14, this peak current is just 64 kiloamps. And if you simulate with X by R less than 14, then it will be less than 64, and more than 14, then this will be more than 64, but it will be definitely less than 70. Even for means maximum X by R, which is infinite, the maximum current, peak current reaches only 70 kiloamps. So when you have a higher X by R ratio in your system, then probably you have to be more careful when you are selecting the circuit breakers. That is, your breaker should have higher making current to handle this maximum peak asymmetrical current because of higher X by R ratio. Then yes, so here you can see X by R is 14 in the left hand side and X by R is infinite on the right hand side. So here probably means you can see there are 3 different currents are plotted against a T. T is for a time, starts from 10 milliseconds. This is in seconds. So the first one is like 10 milliseconds, 20 milliseconds, 30 milliseconds. That's the time step what we have. And this is IB symmetrical. So we have assumed it's a grid. So that is the fault far from the generator. So the symmetrical current remains 25 kiloamps. If you look at the DC current, X by R ratio is 14. So the DC current is exponentially decaying with respect to time. So X by R is 14 and hence IDC value is coming down with respect to time. Since IDC is coming down, though IB symmetrical is constant, IB asymmetrical, which can be calculated using a formula square of IB symmetrical plus square of IDC under the square root. So this IB asymmetrical also changing. And IDC is approaching almost 0 in 300 milliseconds with X by R 14. And probably your IB symmetrical and asymmetrical is almost close, means in less than 100 milliseconds. But if you take the case of X by R infinite, the DC current remains same. Though there is a small slight mismatch. That mismatch is because I am unable to give X by R infinite in the software. So though it takes a large number, but it is not infinite. So that's the reason why there is a slight reduction. But if X by R is infinite, then the IDC, the DC current will not come down. The next question, what's the probable highest X by R ratio? In a reality, there is no system with zero resistance. There is no superconductors available. So R cannot be 0 and hence X by R cannot be infinite. So then what's the X by R ratio which we can assume for the grids? That depends on the upstream systems. So means when you are performing a short circuit study for industries, get this correct X by R ratio from the upstream utilities, utilities in the sense electricity boards or grid authorities or somewhere. So if you have a higher capacity transformers, then your X by R could be higher. If means you have long transmission lines, then this X by R could be less. Okay, this is the simulation results. You can see the first one with the infinite X by R ratio and the second one is with the X by R of 14, where I have plotted phase currents. So if you couldn't really realize this, the next one helps to better understand. I have plotted only DC current here. I have plotted only DC current here. I have plotted DC current with X by R infinite, X by R 50, X by R 14, and X by R 6. So you can see I have plotted for up to 200 milliseconds. With an X by R of infinity, the DC current remains at 40 coulombs. And X by R of 50, the DC current decreases with respect to time. And X by R of 14, it decreases, but much faster than X by R 50. And with an X by R 6, it further reduces much fastly. So lower the X by R, the DC current decays fastly. So higher the X by R, the DC current takes quite higher time to decay. So higher X by R systems, when you're selecting the breaker, you have to be a bit more careful with respect to selection of making current of the breakers. And means higher X by R also results in higher DC currents, and hence means you need to check whether the breakers are capable of breaking this DC currents. Say take an example in the same case, means at 50 milliseconds, assume the relay takes about 50 milliseconds to send a command to the circuit breakers. If X by R is infinity, the breaker has to break 40 coulombs DC current, whereas at X by R 50, this has to break about 30 coulombs. And if it is X by R 14, then probably it has to break only about 10 coulombs. And X by R is 6, then it needs to break only 2 or 3 coulombs. So as I told, the general breakers may have about a 30% DC breaking capacity. You need to check and validate this IDC currents also for selecting the right breakers. So maybe let's coming to the last topic, methods of limiting the fault current. In a system, means existing system, we have selected the switch gears based on the existing systems. But assume there is an addition, like new loads or new generators, then probably the fault current may increase. If this fault current increases beyond the existing switchgear rating, then means we need to replace the switchgears, or probably we have to do something to reduce the fault current below the existing switchgear rating. So means replacing the switchgear results in higher cost and higher downtime, because you need to take it everything, replace it, so there will be higher downtime, which may not be acceptable for a process industries. So here there are some options which has been given how to limit the fault current if it exceeds. In the low voltage system, you can increase the cable length, or you can use unit ratio transformers, or generally in a lighting transformers in commercial buildings. In a medium voltage, you can use current limiting reactors or a series reactors, generally called as CLR. You can use unit ratio transformers. You can use IS limiters. In high voltage, again, you can use current limiting reactors, and you can use network splitting concept. So means like current limiting reactor, transformer, IS limiter, these are all products, but network splitting is a concept which you can apply for high voltage systems or an extra high voltage interconnected systems. So let's have quick examples. So let's talk about an LV. So here we have taken 2.5 MVA transformer. So here if you look at bus 17, that's main, you call it PCC, the fault current is about 50.9 coulombs. If you want to go with less than 50 coulombs breaker, then probably you can slightly increase the impedance. You can increase the impedance and bring down this fault current less than 50 coulombs. But this is possible only during planning stage. This is not possible after the transformer has been manufactured. Okay, take these three cases. Assume that means what to say, this is main switch gear, and my lighting distribution board is about 30 meters from my main switch gear. So I put about 35 square mm cable, and in 30 meters, the fault current has reduced to 11 coulombs. In generally lighting distribution boards, we tend to use MCBs. So most of the time, the standard short circuit rating available for MCB is either 9 coulombs or 10 coulombs. There might be some MCBs which are available more than 10 kilams, but that's not readily available in the market. So if you want to reduce the short circuit current at your lighting distribution board, assume this bus 19 is lighting distribution board. If you want to reduce this fault current less than 10 kilams, then option is, you can see here, I have intentionally increased the line length or cable length from 30 meter to 40 meter. So the fault current came down below 10 kilams. So that means take an alternate route, or probably means what to say, take one more, rotate the cables and intentionally increase the cable length. So just increase in 10 meter cable length of 35 square mm cable will not increase the cost drastically, but that saves means what to say, or reduces the cost of going for 20 kilams lighting distribution board to a 10 kilams lighting distribution board, which is standardly available. There is another option. You can go with a lighting transformer as well. So means here we have considered a 100 kVA lighting transformer, which means what to say, with the same 30 meter length, reduces the fault current drastically to less than 3 kilams. So in a low voltage systems, either you can use of increasing cable length, or you can use a lighting transformer to reduce the fault currents. In a medium voltage, I have taken an example to just showcase an industry which receives the power supply at 110 kV, step down to 11 kV. And in a normal operating conditions, the fault current is 20 kilams, 20.3 kilams. Over the period, assume that the industry brings a new generator to meet their own local requirements, then probably that additionally adds a fault current of 5 kilams. So the total fault current is 25.65 kilams. So originally, when the system is available with an actual fault current of 20 kilams, we might have selected 25 kilams. But in the future, if somebody adds the generator, the fault current exceeds the switchgear rating which we have selected, which is 25 kilams. So how to reduce it? Anyway, the generator is inevitable for the industry to add it for whatever may be their reasons. So you can use first one, CLR, current limiting reactor, or a series reactor, which reduces the short circuit current. So means it reduces the short circuit current from 5 kilams to 3.68 kilams, and hence the total fault current is less than 25 kilams. This is one option. This current limiting reactor, you can add it in just next to transformer as well. The option is yours. But when you are adding this current limiting reactors, that comes with their own drawbacks, like additional reactive power consumption, reduction in voltage, reduction in power factor at grid, etc. There is another option you can use unit transformer. So unit transformer also can be used to reduce the short circuit current. So that's another good option which you can explore. So this if the generator transformer comes in, that has an additional advantages of means what to say, using a delta star grounded, you can prevent the circulating current in this case. Say probably if you take this, means before the generator comes, the high voltage side might be delta and low voltage side might be star. So means if it is star grounded, then probably there could be a circulating current between the generator and the star neutral. But if you go with this unit transformer selection to limit the current, that has an additional advantage of this reduces or eliminates the circulating current. There are other products which are available to limit the fault current in the medium voltage, which is IS limiter, that is from ABB, that is the image at the bottom. And there is a similar product called Clip, that's from G&W Electric. So basically this IS limiter is a fuse. Means if you want to operate two transformers in parallel, means what to say, each transformer contributes some current. Yeah, I think it's saying I have only 10 minutes more. Okay, that's good. So we'll wind up our sessions in 10 minutes. We will not have any further sessions. Means if we need any other sessions, we can plan it in upcoming days. Okay. So means if we want to parallel these two transformers, then that may exceed the switchgear rating. So in that case, probably I can add the IS limiter at the bus coupler. So the IS limiter is nothing but a fuse. That fuse blows in 3 milliseconds. That means before the actual current reaches its maximum value, this fuse blows and isolates the systems and reduce the fault current to a smaller value. So that's what both this IS limiter from ABB and clip from GNW Electric does. And key points to remember for a manual calculation: if you're an engineer, if you do not have simulation softwares, then if you want to still find out the fault current, this is the key difference. I mean, this is the key points which you need to keep in mind. Don't directly use transformer full load current divided by impedance to find out the fault current. You need to use C factor, and you need to use the impedance tolerance of transformer and generator. If you are going to buy a new transformer which is yet to be manufactured, then means what to say, the transformer, you cannot directly take the data sheet impedance, but there is a tolerance which is applicable. So if you ask 8% impedance of the transformer may come up with means plus or minus 10% tolerance. So you need to take negative tolerance of the transformers and generators and the impedance if that is not yet tested at factory. That is, after FAT, factory acceptance test, you can take the actual impedance. But before FAT, that is, if you're in a planning stage, you need to include the tolerance. And many people directly adds impedance. Please don't do that. Always use R plus JX format. So only resistance means if you have two equipments in series, means what to say, don't add Z directly unless otherwise their X by R ratio is same. And as per IEC, you need to consider the correction factors for generators, transformers, and systems like that is kg, kt, etc. And if you have motors, you need to also include the contributions from the motors. And you need to also include the impact of what is the short circuit capacity at your HV side. So these are some key points if you are doing it in a manual calculation. If you do not have a software, that you need to keep it in mind.